जी, बिस्मिल्लाहिर्रहमानिर्रहीम. Welcome to the 13th lecture. Last module हमने कुछ अर्सा पहले किया था. क्या था? Analytical geometry, right? So what we have done is in linear algebra we talked about the nature of linear spaces, right? Whereas in analytical geometry we touched upon measuring those vectors, क्योंकि हमें वो ज़रूरत पड़ेगी उनको quantify करने की, to measure them, to measure their distances, to measure their projections, right? And we saw the benefit of those projections already in machine learning, जो उसका बहुत ही core idea है least squares, fitting, best fitting, right? That's a very early model of best fitting, right? So और बाद में बकिया चीज़ें most of them are like built on those things, yeah. So now we are going into our next module. As I have said, the first module was big. उसमें पूरी हमने we had to establish the foundation, the concepts of vector spaces, all that. Then each module keeps getting smaller because we are picking the concepts we need from there, not the whole thing, right? Each one is a course or a set of courses, right? So of course वो तो we won't do that. What we do is we pick things. So that's why analytical geometry went faster than linear algebra, and these next two modules will go even faster. Then we will come to the second big module. अभी तक जो ये हम कर रहे हैं, this is all in a way it's all linear algebra. Analytical geometry is linear algebra. What we see today is linear algebra. What we see tomorrow, inshallah, is also linear algebra, albeit under different names. Whereas the module that's coming next week, probability, वो पूरी फिर एक और दुनिया है वो, right? Or that combined with this whole linear algebra thing, that is basically what you need to be good at machine learning, right? Programming उसके अलावा है, वो तो skill है, sense है, but from the mathematical side, this is what you need. So today we will look at the how to make the working with matrices and vectors more convenient, right? So in that we have already seen some examples of that. For example, अगर आप याद हो, one of the last topics we discussed last time was pseudo inverse, which is kind of the generalized cousin of the inverse, right? And although inverse was very picky, pseudo inverse says I always exist, right? Because it says, okay, if you can't find the projection within a given subspace of A, find the closest one. तो closest तो मिल ही जाती है ना कुछ ना. So it always existed, and in the end we defined the very general pseudo inverse like this. For special cases, the pseudo inverse had a special form, which I mentioned here. If A has full rank, then the pseudo inverse is simply, instead of inverting A, which you cannot, the reason you go into pseudo inverse is when you cannot find the A inverse, right? It's not square, then the inverse isn't defined. It's not full rank, then although the inverse is defined for a square matrix, but if it's not full rank, the inverse won't exist for that particular square matrix. So there, instead of working with A, we worked with this thing, and we actually saw that this was equivalent to projecting the vector onto the subspace spanned by the columns of A, right? Matrix A. So if A is diagonal, etc. But this was the general case that I briefly mentioned, which says that if A is written as U sigma Vt, then the pseudo inverse is simply V is as it is, U is here, they just switch places, and sigma is replaced by the pseudo inverse of sigma, and sigma is a very easy matrix to work with compared to the general A. So why did we decompose here? That is the one of the questions we will answer today, right? This module will look at that. Also, you saw long ago, अगर आपको याद हो, we had done an experiment where it said, okay, if I give you a matrix A, if it's diagonal, its 100th power is simple, right? 100th power is simply the 100th power of each element on the diagonal. Comes easy. But if it's not, like here, it wasn't diagonal, it was 3, 1, 0, 2. Obviously, 100th power is like matrix multiplications, gets complicated. So we had seen that, okay, what if I can rewrite this guy as similar to a diagonal matrix, right? And we did that, and we found that once we are able to write it like that, then the matter of taking 100th power is simply still same as taking the 100th power of the diagonal elements of a surrogate matrix, kind of proxy matrix, right, AD. But what I did not show you at that time is where did I find these guys that helped me carry out this beautiful diagonalization, right? That is again the subject of today's topic. How do we find these guys? Do they always exist? Yeah. So that is our next module, matrix decomposition. Okay, and as I like to call it, making matrices friendly. It has a lot to do with three things. Why we want to make them friendly? For computation, for manipulation. Computation, give me A times B, and A is a matrix. Give me cosine of matrix A times B. Okay, it becomes complicated. So manipulation is Ax equals B, find B. So I have to invert A, I have to pseudo invert A, I have to manipulate it to get B. Then analysis. This A is like a system acting on the inputs, right? Can you tell me the modes of this system? What kind of behaviors should I expect from this system? If I put it in a feedback loop, would this system become unstable? Will A's powers keep growing, or do they decay? Are there different modes in there I should be aware of? Analysis of the matrix. Now matrices in their general form are not very friendly. पता ही आपको simple multiplication ही headache बन जाती है, right? So these are the things we want to do, and what I call this segment is I love I. Yeah. So of course we all love I, which I am not talking about the self or the ego, although that's a good excuse to bring in my poetry related to that. गुरूर ज़ात में भटका किए हम, बहुत तारीख थी गलियां अना की. अरबी में अना कहते हैं, मी, अना जो इसको अना, मैं, है ना, ये वो अना. So, but of course this is just an excuse to, I am talking about the identity matrix, right? Now this, if you are talking about matrices being computationally friendly, you can't get better than this guy, right? I mean, there is not much not to like about it. Ix is x. Of course, we assume same dimensions. If this is n by n, this is n by 1 or 1 by n. So if it's 1 by n, it's on the other side. Im is mi is m. I to power k is I, right? I inverse is I, and I is diagonal. What's not to like? This is as easy as you can get in computations, right? So our goal would be, what if other matrices could behave like I? Now that's a big ask. It's a very big thing to say. Perhaps that's too much. Maybe हमें पता है ऐसा तो नहीं होता. I give you any matrix A, make it behave like I, friendly हो जाएगा. But can it? Okay. Maybe not exactly as I, क्योंकि I की बड़ी special, unique सी एक है उसकी. Can we pick some features of it? Get close to this. Yeah. Okay. So let's see. This is our goal, making A like I. Now again, making A like I means वो exactly नहीं मिलेगा आपको, right? But let's get close to that. So let's look at the square matrix case, since I is square also. course, this is too much to ask for unless A is equal to I, right? So Ax equals x for all x. So what's the next best thing we could ask for? Could we have something close? What if we say, okay, perhaps let's ask that A pk equals lambda k pk for some vectors. Yeah, अब ये almost थोड़ी हमने उसको गुंजाइश दे दी. You can add lambda, multiply it with lambda, but then you're not required to do it for all x, right? For some, ये थोड़ी सी अब एक हम ज़रा reasonable बात करना शुरू हो गए, right? So let's ask that away. So we are saying perhaps A should behave not as a matrix but as a simple scalar multiplier for some vectors. Yeah. Now this might come close to Ix equals lambda, Ix equals x, right? Again, if it does, at least for these vectors, there is computational gain. A matrix multiplication has simply changed into a scalar multiplication, right? So what about other vectors then, which are not pk? So we say, okay, A behaves almost like identity for some vectors pk, that is lambda k pk, but what about, would that help us for other vectors also? Would this knowledge make it friendly for us for other vectors? क्या है लाभ, या सिर्फ पी के इसको हेल्प मिलेगी? मिल सकती है, कैसे? Basis, good. So let's say perhaps if there are at least n such linearly independent vectors associated with A. So let's say that we do find at least n linearly independent such vectors. We are not saying we want Ax equal lambda x for all x. We are saying at least n such vectors that are linearly independent for which A behaves like this. If that is the case, then any vector x, we have already studied vector spaces. If I give you n linearly independent vectors, by now you know that together they span Rn, right? यही है ना मतलब उनका linear independence क्या होती है? If there are two linear independent vectors, if you bring in a third one, the space dimension increases. अगर increase नहीं हो रही तो linear independent नहीं है. तो अगर 6 दूँ तो फिर उसकी dimension R6 होनी चाहिए. So if I give you n, the dimension is Rn. That means together they span whole of Rn. That means together they can cover any x. कोई भी x को represent कर सकते हैं. So if I can find at least n of them, then I could write any vector x in those coordinates. Before, we are always writing x in the standard coordinates, right? I unit vector के जो columns होते हैं 1 0 0 0 0 0 0 1 0, right? But now I am going to write it in terms of this. How does this help me with the matrix multiplication? So you agree that then Ax is this thing. Now here the magic will happen. क्या होगा अब यहाँ पे आगे अगला step? I still have matrix multiplied by vectors, right? But since the basis, these basis vectors are the eigenvectors, it's simply reduced to, each one is reduced to a simple scalar multiplication. So the whole process of multiplying A with x has simply reduced to scaling alpha, alpha 1, alpha 2, alpha 3, right? Of course, I will have to first one time find the projection, right? A1, A2, वो मुझे नहीं, we will see an efficient way for that. So that means that our strategy might be working. So if we require if we say okay, AP has to be lambda p for at least n vectors, linearly independent vectors. If I can find that, then my job becomes easier, not just for P1, P2, Pn, but for any vector x. Yeah. Would it help with other operations as well? Okay, let's see. let's write this n linear independent special vectors. Yeah. So can I make n equations like this? I'm working on the assumption that A has associated with it n such vectors that it can be written like that. Yeah, linearly independent vectors. So if I write n equations, I can put that in matrix form. First, let's give these some names instead of calling them special vectors all the time. Let's call them eigenvectors of A, and the associated scalings we will call eigenvalues of A, right? Again, this was driven by our thought of having A behave like I identity. So I says Ix equals x, but we said that's too strong. We cannot give you that. What we can give you is AP equals lambda P. Yeah, and if that happens to happen for at least n linearly independent vectors, it will not always happen. Okay, वो वाले A फिर friendly होने को तैयार नहीं, क्या हम उन्हें छोड़ देंगे? No. we couldn't find the inverse, we found the pseudo inverse. Similarly here, if we can't do that, we will find the nearest match. Okay, so eigen is German word meaning characteristic, self, or own. Yeah, so these are the characteristic vectors of A or the own vectors of A. Why are they like that? Because every A, the choice of A will have its own vectors. Yeah, सिर्फ I है जिसके लिए हर vector eigen vector है, right? But for all others, they have their अपना टोला उनका, right? So now if I write it out, if I write n equations, I can make it a matrix form, right? कैसे होगा ये? AP1, it's basically, it's like A, P1, P2, P3, P up to Pn. These, if I have n of them, right? Each vector now here is one eigenvector of A. I can put them, all of them together in one matrix and call it P. So the columns of P are the eigenvectors of A, right? And of course you can see this P here coming from here. But what is this guy, the big lambda? ये भी capital lambda hai, loves, right? It's also lambda but capital one. Yeah. This lambda, what does this represent? Eigenvalues. अगर आप, if you try out the matrix multiplication, you will find that this is one way you can do that. Lambda 1, lambda 2 to lambda n. So this guy contains this. But notice we have AP equals P times lambda. In a way, this lambda is going to behave as a proxy of A, but a friendly proxy. Notice it's diagonal. वो जो हम चले थे जहाँ से कि identity कितना अच्छा है, diagonal है, Ix equals x. So we are getting close to all that, right? So yeah, lambda contains the eigenvalues. Yes, this is the eigenvalue corresponding to the first column. Yeah, the first eigenvector in P. This is the eigenvalue corresponding to the second. तो जिस order में वो है इसी में इसको रखना है. Yeah. So how does this help make A like I? Let's see. First notice, let's call this the eigen decomposition of n by n matrix A that has n independent vectors that we can use to form P. यहाँ से ये समझ आ गया है ये, from here I can simply multiply both sides by P inverse, right? The P inverse exists. Why? क्यों exist करेगा? The inverse? Because we have started with that assumption. It's an n by n matrix and each column is independent of the rest. We started with that assumption. That also gives you a hint. If you cannot find, or there do not exist at least n independent eigenvectors connected to a matrix, then the matrix cannot be written this form. We say the matrix cannot be eigen decomposed. We say the matrix cannot be diagonalized. We say the matrix is not equivalent or similar to an डायगोनल मैट्रिक्स, कई नाम है इस बात के, राइट. उसके लिए हमारे पास फिर जुगाड़ है लीस्ट स्क्वायर्स वाली, we'll come to that, but as long as we have that, note that A's surrogate or A's proxy, the lambda is diagonal, right, है वो diagonal है. फिर note, very nice, powers become very simple. It's not like you have to take the kth power of p also. Because of that formulation you can verify that if you keep multiplying a square, a cube, p and p inverse will keep cancelling each other out, and you will be left with only this guy. Not only this guy, but most importantly, if this wasn't diagonal, we will still be stuck, but this is diagonal. So lambda k is simply the kth powers of lambda. वो जो i k equals i बन जाता है for kth power, आप i की वो 1 1 आ जाती है. This is as close as you can get to that. Inverse becomes very simple, right. So if I give you this eigen decomposition and ask you to find A inverse, you know what is the inverse? Simply in diagonal elements को उल्टा कर दें, invert कर दें. Given that all of them are non-zero, if any of them happen to be zero, then you have already concluded that matrix A is non-invertible. तो फिर आप attempt ही ना करें उसको, right. So but the inverse, such a huge pain for matrices, becomes a simple matter of inverting scalars, right. So in fact it can be shown that for any polynomial function, matrices के भी हम function बनाते हैं ऐसे, this one. So if you apply a polynomial function to a matrix A, that means you will have here a naught, small a naught plus a1 times matrix A plus a2 times matrix A square and so on. That becomes so simple. See, these guys play no role. F A is simply the same function applied to the lambda, which is diagonal. So it's actually just applying it to the diagonal elements. That's it. Achhi khasi classes of functions, exponent of A, matrix raised to an exponent, becomes simply the diagonal elements raised to exponent. Well, it's a huge powerful thing, and it seems we have achieved something which we started to set out, was to make A computationally friendly, right. So so here's our magic formula. Of course it comes with with the condition that there are at least n linearly independent eigenvectors associated with A, right. What if it does not have those? I've already mentioned that. Firstly, if it does not, we call A defective. This is different from rank deficient. Rank deficient क्या था? A is rank deficient if if it's square, the columns of A are not linearly independent, right. So defective is A cannot be eigen decomposed, okay. So you can compare their different things. We won't leave it there, we will try to find the closest decomposition that is possible, okay, and we will come to that later. So you might ask, okay, how did this happen? How did A start behaving like I when it was eigen? Mathematically I have shown you, that's where we started, right. Ax equals lambda x. So we started with that kind of thing, but geographically, okay, we can also see geometrically, sorry. Let's take a quick formal introduction to the eigenworld. You know, when a vector is multiplied by a matrix, it's like it's being operated upon by a system, linear system, which is A, right. So this linear system A in general not only changes the magnitude of the vector, it also changes its direction, right. I change नहीं करता, ना magnitude change करता है, ना direction change करता है, but other matrices have to do something, so they do this. X has been enlarged and also been thrown off the line it was on. So it was here, Ax is bigger and no longer on this line, it has been thrown off its axis, right? So however, there might be special vectors associated with the matrix where this does not happen, right? So there might be vectors, for example P1, so that when P1 is multiplied by A, it does not throw it off its axis, keeps it there, only scales it. And notice this is what we defined for our computational ease. We said, okay, AP had to be equal to lambda P. This is what we were requiring. Find me the vectors for which A behaves as a simple scaling factor, doesn't do anything else to it. So we call them the eigenvectors of A. Of course, if lambda 1 is negative, direction will change to by 180 degree. Lekin it stays on that line, right? So it's not correct to say that eigenvector वो होता है इसकी direction change नहीं होती. It can flip, but only that. दाएं बाएं नहीं होगा. Yeah. So what happens now is that for this is a 2D case. Yeah. If there exists at least one more linearly independent vector, which is linearly independent from the first one. Now linear independence does not require orthogonality. अक्सर आप लोग यही सोचते हैं 90 degree, but that's not required. क्या required है? Dimension should increase. If alone this guy is represented a line as a subspace, and you bring another vector in, and the subspace changes to plane, एक dimension add हो जाए उसमें, then that vector is linearly independent of the first one. अगर नहीं change होती, increase नहीं होती, then it's not. Yeah. So it's not orthogonality, it's linear independence that's required. So if I could find another vector, and in this case it seems it might be there is another one. So this matrix has at least two vectors associated with it, for which it behaves as a simple scalar. It keeps them on their axis, right? So this matrix is saying that I don't like your 0 1 and 1 0, right? That is what your x is written in. It's saying I like these. So why not write all the vectors in terms of these? So why not form a new grid? So we are used to this grid, ये जो rectangular grid है, right? We try to solve everything in this grid, but this matrix is saying I am more comfortable with another grid which is a rotated sheared version. ये जो अब नया grid बन गया, नजर आ रहा है? It's saying if you treat this grid as my world, then I will behave very much like identity, right? Identity can behave very much like identity in all grids, क्योंकि उसके लिए तो Ix equals x for all x, right? तो वो तो एक बहुत ही unique case है. But for matrix A, it's saying in this world, not this one, this rectangular grid, in this special grid formed by P1 and P2, I can behave very much like identity. So अब हम already change of basis पढ़ चुके हैं, right? So all we have to do is find a way to convert our vectors, change their basis to the basis that A likes, which are based on at least two of its linearly independent eigenvectors, and there it will act like this. So it's basically saying, okay, now if instead of giving me x like this, yeah, which is these coordinates that you read, basically you normally read them on the rectangular grid, ऐसा ही है, which will be basically 1 here and 2 here. Yeah, so you would read x as 1 2, 1 along x, 2 along y. But it's saying no, don't read it to me like that. My world is not made of this gray grid, it's made of this blue grid. What is the values on the blue grid? If you read on the blue grid, एक ये बनता है इसका कोऑर्डिनेट, पढ़ना आता है वो थोड़ा सा डायगोनल पे, या जस्ट थोड़ा सा इमेजिन करना पड़े, but it's this value here which is alpha 2 p2 and So x has its different coordinates here. ये coordinates read करें. If you give me those, I will simply scale them. Right? Now read off. आपने अपनी दुनिया में पढ़ना है. Yeah. So okay, I have scaled them. Read them off in your world, which is here. Oops. So read them off here. ये जो आपकी values आ रही हैं, that is the answer. Right? So this is what it's doing. It's only saying change the bases, bring your vectors from the standard notation to the my preferred notation, my preferred basis, and there I will just behave as. And this is what we did basically, right? Now mathematically we wrote an x in terms of those. We were doing exactly that. So it turns out that all A requires to start behaving or become more friendly is a change of basis where possible. And this is what the eigen decomposition is doing. If you recall, थोड़ा सा दोबारा देख लेना slides वगैरह on the transition matrix. Remember, we had defined precisely how to write the transition matrix of going from one basis to another. It was simply क्या था, source की जो write the basis of the source in terms of basis of the destination, right? बड़ा simple सा उसका तरीका. So this is what you are actually doing. So this is what's happening. This matrix is a transition matrix from the standard basis to the basis preferred by A, which are in P. This is changing to those. Once you are in this world by the change of basis, then A's proxy acts on the vector, जो भी x आएगा यहाँ पे, and that is diagonal. So almost identity वाला काम हो गया. But once it's done, it knows if you want Ax, then you want the final output in the standard notation, right? So ये इसका inverse है. It's a change of basis, reverse transition from P to the standard basis, right? Then it gives you the answer in the standard basis. So in summary, this is what A is saying. If you want A to be multiplied by x and you want A to behave as much as like identity, it says bring x, change the basis of x from standard to my preferred ones, yeah, which is carried out by P inverse. Once you are there, it behaves as a diagonal nice matrix, just scales them, kuch aur nahi karta, yeah, does that. Once it's done doing that, it says okay, to give you your answer in the standard basis, which is the way, I will, whatever I have done to this guy, I will reformulate that in the standard basis, which is now carried out by P. This is a reverse thing. So yes, this is what it does, and that's why it was working. So basically these are then, this is matrix P, and these two were actually, we didn't mention that before clearly, but these were the eigenvectors of the matrix A that we were trying to diagonalize. So that was an intuitive understanding of the whole idea. Now we need to add some nitty-gritties here. So eigenvector of a square matrix A, a vector that passes through matrix A unchanged except for scaling, which is what we are saying there, AV equals lambda V. Eigenvalue is the scaling associated with it. So here W is not an eigenvector of A. Why? Because W was here, when it was multiplied with A, it rotated, whereas V is an eigenvector, it stayed on the same axis, right? So each square matrix will in general have its own set of eigenvectors. That's why the word eigen, the German word own. For an identity matrix, yes, every vector of matching size is an eigenvector because it's Ix equals x. Yeah. So again, mathematical definition, ये पता यहाँ से शुरू होता है normally Ax equals lambda x, right? But I think formulas should only come after the intuitive development. Yeah, the necessity there is. So square matrix is defective if it possesses fewer than n linearly independent eigenvectors. There is a result that helps us conclude if the matrix is defective. If there are, if it has n distinct eigenvalues, then the eigenvectors associated with those eigenvalues will always be linearly independent. Okay, so it helps us. Okay, if you give me a matrix, n by n matrix, and I find that it has n distinct, at least n distinct eigenvalues, then I can be sure that it has n distinct linearly independent eigenvectors. That means I can be sure it can be diagonalized, can be eigendecomposed, all those things that we did before. Yeah, famous is eigenvectors are not unique, everybody knows. If P is an eigenvector, so is Cp. कैसे? You said AP equals lambda P. So A times C times P will have to be lambda times C times P. So of course, but you can always make them unique by putting a condition on the norm. जिनका unit norm है, unit length रखते हैं, वो तो फिर unique होते जाएंगे, right? So it's not a restrictive thing. It's just good to know that if P is an eigenvector, so is Cp, although with a different eigenvalue. वो क्या हो जाएगी? Lambda times C. Eigenvalue relationship with these guys, determinant and trace. Determinant याद है? Matrix स्कूल में भी पढ़ते हैं, फिर अंडर क्या होता है? So it has a special definition, right? बड़ी घूमी फिरी सी है, रिकर्सिव सी definition है. First it's for a 2 by 2 matrix, ऐसे multiply करके, फिर ऐसे multiply करके, फिर minus कर दें, फिर उस चीज़ को higher level पे repeat करते हैं. So it has a kind of a recursive definition, ऐसे ही है ना? And इसका role कहाँ आता है? Where do we use it often? Finding the inverse and also finding if the inverse exists, right? क्या होता था वो? Inverse से determinant का क्या link था? So inverse does not exist, right? And of course, like the inverse, determinant is defined for square matrices only. Yeah. So now it has a very special relationship with eigenvalues, and there it is. The determinant of a matrix, it turns out, is simply the product of its eigenvalues. Yeah. Trace क्या होता था? Sum, but what is trace before sum of eigenvalues? Trace of a matrix? A matrix क्या होता है? Sum of the yes. So trace of a matrix is the sum of the diagonal elements, right? And in terms of eigenvalues, it is simply the sum of the eigenvalues of the matrix. Just as a reminder, it's determinant of a square matrix calculated in a special way. इसकी graphical understanding क्या होती है determinant की? It's the volume 3D में अगर देख रहे हैं, of course 4D would mean 4D volume जो भी बनती है. It's the volume formed by the columns of the matrix. Okay, so if a matrix has columns R, B, G, then the volume, the parallelepiped, ये बड़ा मुश्किल सा लफ्ज़ है, पता नहीं कितने L और P हैं इसके अंदर. But anyway, this thing formed by it, that is the volume. But now knowing this, क्या कुछ समझ आती है? Why determinant has to be non-zero for inverse to exist, right? You can already get an idea. Imagine if R, जो तीसरा vector, was in the subspace of B and G. B and G की subspace क्या है? एक plane है, ऐसा ना? If R had been in there, what would be the volume of this? 0. If R had been in the subspace of B and G, that means that the 3 columns of the vector are not linearly independent. That means we already know it does not have an inverse. Now this also tells us that the volume will collapse, right? So determinant will collapse to 0, which also again reinforces our understanding that the matrix will be non-invertible. Yeah. So this formula should be used with care. It assumes that the determinant is not 0. Yeah, अगर वो 0 है तो ये formula आप नहीं लिख सकते. So if it does exist, yeah, for n square it is invertible if and only if determinant of A is not equal to 0, which is equivalent to the linear independence requirement जो मैंने आपको बताया. If they were not linearly independent, one of them will be in the plane of the other and the volume would always collapse, right? If it collapses to 0, then again we don't have it. Yeah, we know this fine. So knowing that determinant is the product of eigenvalues, ये तो हमने कहा, trace is the sum of eigenvalues. असल में trace होता है sum of the diagonal, but it's equivalent to the sum of the eigenvalues, and determinant is the product. So what can you say about product? We can state about terms of eigenvalues of A. Can you talk about invertibility of a matrix in terms of its eigenvalues? क्या requirement होनी चाहिए? नहीं, eigenvalues का है, वो तो basic definition. Now I want you to relate that to eigenvalues. Bridge क्या है? We already saw that the determinant is the product of eigenvalues. ऐसे ही है? आप बताएं. हाँ, क्या होना चाहिए? कितने लैम्डा 0 नहीं होने चाहिए? एक भी 0 नहीं होना चाहिए. None of the eigenvalues should be, क्योंकि प्रोडक्ट है ना, एक भी काम खराब कर देगा. एक से ज़्यादा हो फिर तो गया, वैसे ही गया, लेकिन एक से भी गया. So in a way you can relate this now to the eigenvalues. None of the eigenvalues should be 0, then the matrix is invertible, which is effectively all of these things put together. Yeah. Yeah, there are some statements good to read offline. कोई इतना मसला नहीं है. Lambda is an eigenvalue of A. Rank of A minus lambda in is less than n, and determinant of A minus lambda in is equal to 0. Okay. Basically you are saying that A minus lambda I n times x should be equal to 0, right? So because of that we have this. Some other rules good to remember. ये सिर्फ reminder है. Determinant of a product is simply the separate determinants. Determinant of the transpose is invariant, so same रहता है. Determinant of an inverse, if the inverse exists, is 1 over the determinant of the matrix. And some other rules for determinant, just reminder के लिए मैं डाल दिया, you can read up. Trace, as we said, is actually the sum of the diagonal elements. It also has some nice properties. Trace A plus B is trace A plus trace B. Trace of in is n, so on. But this is a good result that the trace is commutative. Yeah. Trace AB equals trace BA, assuming that AB, BA both are defined. Yeah. That leads us to a very interesting result, which is this, that the trace of similar matrices is always same. Similar यही था ना मेरे, B can be written as S inverse AS. So interestingly, the consequence of trace AB equal trace BA can be extended to trace AKL equal trace KLA, and that can be extended to this thing. So similar matrices have the same trace. We will come back to this soon. Very closely related to the study of eigenvalues of a matrix is the characteristic polynomial of the matrix. याद है पढ़ा हुआ? So you must have heard of it. So nth order it's basically an nth order polynomial in lambda. There it is. It's the determinant of a minus lambda I. It can be shown that it's just a kind of a polynomial in lambda. Okay. The last two terms have relation to determinant and trace. You can find that out if you want, but this is it. Lambda is an eigenvalue of A if and only if lambda is a root. अब ये nth order equation है, कितने roots हैं? N है, right? There is nothing saying that the roots cannot be repeated. So a matrix, multiple eigenvalues may show, same eigenvalue may show up multiple times, although they might be associated with different eigenvectors. कोई restriction नहीं है. Yeah, because it's a polynomial here. So we could write it in factorized form, looks nicer. वो power form जो है वो थोड़ी सी चलती जाती है. So if we factorized form में लिखें, then you can already see that the eigenvalues of this matrix are lambda 1, lambda 2, so on, lambda n. But if we want to account for repetitions, maybe lambda 2 is the same as lambda 1. कहीं लिखा तो नहीं हुआ. nth order polynomial है, n roots चाहिए, कोई नहीं कह रहा कि वो different होनी चाहिए. Distinct roots are not guaranteed. So we could account for repetitions by writing the formula like this, where we are saying that there are in fact only d distinct roots. Of course total उनका n ही होना चाहिए, क्योंकि ये तो fundamental theorem of algebra है. nth order polynomial n solutions देगा आपको, right? So in fact we have a name for this. We call the algebraic multiplicity of an eigenvalue. Is basically how many times it shows up for a given matrix. Okay, इसकी फिर कुछ आगे analysis में काम आता है. Eigenspace and eigenspectrum of a square matrix. So basically I'm more interested in the eigenspectrum. Eigenspectrum of a matrix, if you give me all the, so if you tell me A has these eigenvalues lambda 1, lambda 2, lambda 3, lambda n, then these together are the eigenspectrum of this matrix A. Okay. Eigenspace is basically associated with the with eigenvectors. So for example, let's say it has this matrix lambda 1 and lambda 2, let's say, or lambda 1 has 3 eigenvectors, 4 eigenvectors associated with it. Then those eigenvectors form the eigenspace associated with lambda 1. Okay, that's it. इसमें कोई special नहीं है. Then we have the concept of geometric multiplicity. So one eigenvalue might show up several times. It may show up with different eigenvectors which may or may not be linearly independent. But the number of linearly independent eigenvectors associated with the given eigenvalue are its geometric multiplicity. Okay? ये मैं इसलिए आपको बता रहा हूँ for the sake of completion, because in some theorems these will show up, that the geometric multiplication has to be this much, then this is invertible, or then this will happen. So थोड़ा सा पता होना चाहिए. Algebraic multiplicity is simple. How many times the eigenvalue shows up in the polynomial, the characteristic polynomial, right? जबकि geometric multiplicity is how many, for a given, अब आपकी एक vector है, उसका एक eigenvalue है 2. Then let's say you find that there are होंगे तो इन्फिनिट, वैसे वो मल्टीपल्स भी हैं, उनको निकाल दें. How many linearly independent eigenvectors associated with 2? That is the geometric multiplicity of 2, this eigenvalue 2. Relationship with linear mappings. Linear mappings yaad hai, we did that in vector space. So it turns out that if you remember, for a linear mapping T phi, there was associated a matrix A phi, right? But the matrix wasn't unique, right? It depended on the choice of bases. Bases change karte jaye, nahi form aa. So it wasn't unique. The beauty of these three parameters, eigenvalue, determinant and trace, is that they are unique for a linear mapping. वो क्यों होगा? If you remember, we said that two different, अगर आपको याद हो, we had written that if A phi is the matrix related to a linear mapping, we called it the transformation matrix, then change of basis matrix was some T inverse A phi T. Yaad hai? We change the basis like this. But we already know, for example, that the eigenvalues of this and this have to be the same. Their determinant has to be same. Their trace has to be same. So that means these three things are invariant to the selection of bases. They don't care. Okay, so they are unique to each linear mapping. That is often helpful in characterizing linear mappings. So this is what I said. Relationship with diagonalizability. Firstly, we say a matrix A is diagonalizable if it is similar to a diagonal matrix, right? That means if it can be written as D equals P inverse AP, where D is diagonal. Yeah, and we already said that if a matrix A, square matrix A, has at least n independent eigenvectors associated with it, then it can always be written in this form. That means it's the same thing as saying that this matrix is diagonalizable. Meaning, saying that a matrix is eigendecomposable is the same as saying that it is diagonalizable, right? So this is a diagonal matrix. Okay, but what about helping with analysis? I said at the start why we want to make the matrix friendly. We want also not just computations, not just manipulations, but also analysis. So we already saw several important relationships: eigenvalues, determinant, trace, invertibility. If even one of the eigenvalues turn out to be 0, forget about invertibility, right? So some things like that. So it's already helping us with analysis. In addition, characteristic equation associated with a matrix, where the eigenvalues are also lying, is actually a very special way of studying different modes of a matrix or the system represented by the matrix. Yeah. So that is related to the concept of eigenfunctions. Eigenfunctions, what are they? They are a special kind of eigenvectors, right? But they are written in terms of linear operators. Yeah. So eigenfunction क्या होता है? And how does Fourier chain calculus to algebra? That is what it does. Just like eigenvalue ने क्या किया था? Ax equals lambda x हो गया था. So a matrix multiplication, which was a linear operation, changed into a simple scalar multiplication, right? So now let's see. We could see a matrix as a system operating on a input, right? Matrix A is a system that operates on x and gives you y. So you could write it as gt equals sft, for example. Now an eigenfunction of a linear operator is a function that goes through S with only a change in scaling. So if it goes through, it comes up. Now you know already that integration and differentiation are linear operators, right? What is their eigenfunction? ये इसको मीट करेगा. So if you pass the function through this system, the function comes out as it is except for a scaling. तो कौन सा फंक्शन है जो डेरिवेटिव और इंटेग्रल से ऐसे ही गुजरता जाता है? बता दो आप. एक्सपोनेंशियल है ना, राइट. e टू पावर x, e टू लैम्डा x का क्या है डेरिवेटिव? लैम्डा e लैम्डा x. So the eigenvalue is lambda now and e lambda x is back. What's the integral? Again same thing. So we already know that these guys are linear operators and the complex exponential is an eigen function of these guys. So if we can use that, this is what Fourier transform really does. It says, okay, remember हमने कहा था कि instead of doing ax, which is multiplying matrix multiplication, I will write x as alpha 1 p1 plus alpha 2 p2 in terms of eigen vectors. If I had done that, I don't need ax. I just need alpha 1 times lambda 1, alpha 2 times lambda 2. I have replaced this whole linear operator, big linear operator, with simple scalar operators, right? Now this is what Fourier is going to do, but with functions. These guys derivative and integral are linear operators. I know their eigenfunction now, which is complex exponential. So what I'm going to do is this. First let's see what the direct approach does. It leads to calculus. So we already know if this is the impulse response of the system, then the output of the linear system, we saw this before, ये थी convolution, yeah, that's an integral. But if you use eigenfunctions, you don't need to do this integration thing. You will end up with, so using the idea that these complex exponentials with Fourier uses a subset of that. पूरे सारे complex exponentials are eigenfunctions of linear operators, which means they are eigenfunctions of integral and calculus, differential. But Fourier uses the complex sinusoids in there, yeah, जो कि pure ना damp होते हैं ना grow करते हैं, right? So it uses, instead of e lambda t, where lambda could be sigma j omega, it just uses the j omega part, sigma को 0 कर देते हैं. So it uses that part. It says, okay, I will write my xt in terms of these bases. वही जो हम कर रहे थे कि x was alpha 1 p1 plus alpha 2 p2, ये उसका, it's making a continuous sum of that. ये वही कर रहा ना. It has these eigen functions as bases and it's just finding alpha 1, alpha 2, 1, 2 मुराद ये omega, yeah, it's a function of that. But once it does that, we know that Ej omega will pass through as h omega Ej omega, right? So then जैसे alpha 1 times lambda 1 alpha plus alpha 2 times lambda 2, that happened, same thing will happen here, right? They will just, the eigenvalues and the projection values will get multiplied. You don't need any special calculus to solve this, yeah. So Fourier, what's the difference between Fourier, Laplace, wavelet? They use, Laplace uses the whole e lambda t. Okay, it allows for scale, growth of the sinusoids and the decay of the sinusoid. Okay, so it can handle unstable systems. Fourier is for stable systems. So if we see A as a linear system, its characteristic polynomial and eigenvalue can help us see its different modes. We can try to see, okay, which of these are dominant in the behavior of A, which of these are larger. So if I have a feedback system where A's powers are being increased, A square, A cube and so on, then I can, from this polynomial, I can already see that the larger eigenvalues will take over, वो dominant modes बन जाएंगे उसके, yeah. So you could see, okay, how the different modes, how the different sinusoids are going to pass through this system. And in fact, this is the question that Fourier was trying to answer when he came up with this formulation that we now call Fourier transform. And the concept of eigenvectors also comes from eigenfunctions. हम उल्टा पढ़े ना, लेकिन असल में इधर से आता है, ठीक है. So it goes from eigenfunctions to eigenvectors. So what if A is defective or not even square? अभी तक तो we had this कि A is square and A is not defective. That means A has at least n linearly independent eigenvectors associated with it. When it had those eigenvectors associated with it, what did we do? We projected, आप मुझे कोई भी वेक्टर दें उसी dimension का, of course n by n है तो n by 1 का वेक्टर देंगे. I will project that vector onto its basis, right, and work with that projection. Yeah, but what if वो है ही नहीं है, 3 independent है ही नहीं, what can we do? क्या करेंगे, घर चले जाएं, right? What we can do is exactly what we did in case of pseudo inverse. Said, okay, I cannot find you 3 of them, but I can find 2 independent and a third slightly dependent, as close I can get to being independent. Okay, so and I let you project onto those 3. Okay, so just like we did from inverse to pseudo inverse, we will go from eigenvalue decomposition to something called singular value decomposition. And just like here again, the idea is, okay, I don't have those nice eigenbases for you to project your x onto, but I'll give you the next best thing. I'll give you 3 lines projecting onto which will minimize the error, just the closest you can get. Okay, so of course it's not nice to ask Ax to be lambda x, क्योंकि देखिए, if A is non-square, it's not just scaling or doing something to multiplying x or changing its direction, it's also even changing its dimension. Let's not just कि ये उसको scale और rotate कर रहा है, इसकी dimension भी change कर, अगर वो 2D में था तो उसको 3D में ला रहा है शायद, और अगर 3D में था तो उसको collapse करके, because it's m by n, it's taking in Rn and giving me Rm. So asking it to act like this now is too much, कि Ax equal lambda x, क्योंकि even dimension भी change होनी है उसकी. So what's the next best thing? Okay, what if we could ask it to give me AV equals sigma u, where V is n by 1, which is what A has, A takes n by 1, and u is m by 1. बड़ा interesting सा error आ रहा है, ये इधर चला गया, actually the same thing. Okay, so I don't have any eigenvectors which could be used as the basis, but just like pseudo inverse, I could do the next best thing. I could give you, I say, okay, I'll find the next best vector projecting onto which minimizes this thing. ये वही least squares है दोबारा. Okay, so I don't have those 3 independent ones, but I'll give you 3 those that projecting onto them is the next best thing you can do. So how do we achieve that? Basically we are saying, okay, find me a vector v1 such that the among all the possible vectors v, the AV I get for this v1 is maximum, yeah, which is effectively saying, give me the maximum projection you can give. Okay, why we require V to be unit norm, because we want them to act as bases, so we force them, क्योंकि वरना वो अब बता, if V satisfies it, maybe it's 2 times V will also satisfy, 3 times, तो ये तो बड़ी unsolvable सी problem है और सब ने देनी एक ही line है, तो why not force it to be unit norm. So we take away this idea कि वो V ये line हमें चाहिए, we don't care कि वो इतनी बड़ी है इतनी बड़ी इतनी बड़ी, right. So let's fix it to unit norm so that the problem is simplified. And by the way, that vector you give me, I will call that the first singular vector, and the maximum projection I get, I will call it the singular value of A. Okay, and then I will repeat. अगले vector के लिए क्या requirement होनी चाहिए? It should be orthogonal to V1, right, and be the next best projector for A, yeah, AV. So if you keep repeating that, yeah, I already said we'll call them singular values and vectors. Will this procedure work? There is a theorem that says yes. Okay, so this procedure will always give you the best possible subspace. Okay. Okay, but remember, for the square case we got a nice decomposition like this, बड़ी अच्छी एक clean सी आ गई थी. The question is, can we get something like this for non-square or defective matrices? So much like pseudo inverse, we could do that if we work with ATA or AAT instead of, there is a special theorem, spectral theorem. It says that a symmetric matrix, give me a symmetric matrix, of course then it has to be square, right. A symmetric matrix always has an orthonormal basis for the, basically it's saying that a symmetric matrix can always be eigen decomposed. Okay, so how does that help me? Yeah, that is fine. Symmetric matrix आएगा कहाँ से? Yeah, so there it is. Give me any matrix m by n, कोई requirement नहीं आपकी तरफ, ठीक है. Give me any matrix m by n. ATA will be symmetric. Now if ATA is symmetric, the spectral theorem says that ATA can always be eigen decomposed. Okay, so instead of working with, rather pseudo inverse भी यही कर रहा था ना, instead of working with A, it was working with ATA like this, ATA inverse A something, yeah. So ये बिल्कुल इसका parallel है ये, yeah. So instead of working with non-square A, we will work with ATA, and this says that it can always be eigen decomposed. That means ATA, not A. ATA can always be written as PD, PT. अच्छा, eigen decomposition जो हम पहले कर रहे थे उसमें यहाँ inverse था, yeah, but because of the symmetry, actually now this is the P inverse is actually PT. Okay, so this thing now contains the eigenvectors of what? ATA, and these are the eigenvalues of ATA. This is what we will call the singular values and singular vectors of A. वो जो हमने अभी पहले interpretation निकाली थी, that is equivalent to this thing. Okay, so this is what the singular value decomposition looks like. Yes, if the matrix is square and non-defective, you can write it as P lambda P inverse, eigen decomposition. But if it is not, then you don't get that nice thing. What you get that nice thing for ATA, but not for A. What do you get for A? For A you get this thing, which is the next best thing, U sigma V. Of course, if it is m by n, then the last one has to be m by m. This is m by n, and this is n by n. Okay. Now U and V are orthogonal matrices. याद है orthogonal, इनके their columns are orthonormal. That basically means that U equals I, and VT V equals I. Okay. Now this is a very powerful remark. The SVD exists for any matrix A. just like pseudo inverse. So why is that? Singular values, let's see. Yeah, first we'll call these the left singular values and the right singular values. Right singular values, left singular values of A, and this guy contains the singular values. Sigma की shape क्या है? It's not rectangular. Lambda was rectangular and diagonal, yeah, but it's the next best thing. Look, it is diagonal plus जो additional dimensions चाहिए, they are zeros. Okay. Similarly, if m is less than n, it is diagonal and the additional dimensions are zeros. This is the closest I can get for you for m by n for non-square matrix. इससे ज़्यादा आप डिमांड नहीं कर सकते क्योंकि वो dimensions ही आप change कर रहे हैं. So how are the eigenvalues and the singular values connected? I already mentioned that. If you look at this now and look at the hoped for eigen decomposition, we said A can be written as U sigma V T, if it can be written like that. Then if I expand this out, you can read this is identity, right? It becomes this. So what is the relation between P and V then? क्या है? The eigenvalues of ATA are the left singular vectors of this guy. VT is PT and sigma I square is lambda I. Lambda I are the eigenvalues of ATA, not A. Yeah? Sigma I square are the singular values of A. So effectively, I haven't shown it fully, but actually this shows us that the proposed SVD is justified because spectral theorem already told us we could do this, and our decomposition led us back to that, so it means it's always doable. समझ आई? थोड़ा सा ये roundabout way, but effectively we are saying, okay, from now on, if you give me a non-square matrix, I will say, okay, I cannot give you AX equals lambda x or AP1 equals lambda P1 for some P, so let's say PK. What I can give you, next best thing is AVI equals sigma I UI for I equal 1 to R. R अब क्या है? R is basically the rank of A, of the matrix. Okay, so and इसको if I write it out, this is what I get. A is U sigma V T. So now instead of P lambda P inverse, I have U sigma V T. And what it is saying now, अब इसमें वही बातें हैं, सिर्फ ये है, there is an additional step. There is a change of dimensions. क्योंकि m by n है ना, input n लेना है, output m देना है, m by 1. So it's saying, okay, give me a vector x. What I'll do is, of course, x has to be n by 1 if A is m by n. I will change its basis to the basis I prefer. There I will act on it almost like a diagonal matrix as much as possible, and then I will, अच्छा यहाँ पे ये it's not only gonna act on it as a diagonal, but वो जो extra zeros थे ना, they are going to carry out a change of dimensions from n to m. Once it's done, I will give you back in the Rm, I will give you back from my notation to this thing. So basically this is what it's doing. Graphically it makes more sense. If A is this thing, अब ये किस dimension के vectors लेता है A? ऐसे मल्टीप्लाई 2 by 1 के, राइट? 2D vectors लेता है और देता आउटपुट में क्या है? 3D vectors, right? So if I put all those vectors that I want to process through A in a matrix called X, so let's see what happens to that. X is a 2D, right? So it has all those 2 by 1 vectors इसके अंदर पड़े हैं, हर column इसका एक vector है, yeah? When it gets multiplied with A, what really happens is, अगर आप right पे देखें यहाँ पे, what is happening to x? पहला step क्या हो रहा है? That's a change of basis within R2. ठीक है? So it's changing basis to the preferred basis of A. उसमें ले गया. Then it's going to multiply with sigma, which is scaling. उसमें sigmas थे ना, scales पड़े हुए थे, plus additional dimensions थी. Yeah? It's scaling and bringing it into 3D now. Yeah? क्योंकि आंसर इसने 3D आंसर देना है A ने. Then in the 3D, this U brings you back to the standard basis. Yeah, so you are back in standard basis, and this is what happens. So you can read up on this, how SVD and EVD compare with each other. For if A is symmetric already, एक तो था हमने A से ATA बनाया था, if A is not square and defective, but if A is actually symmetric, which means it is square and symmetric, then eigenvalue and eigen singular value become exactly same thing निकलेंगे वो, ठीक है? So you won't need to go there. One application of SVD, do we need the whole matrix? If we look at this SVD formulation, right, contains a special insight. What's that? You can rewrite A U sigma VT as this thing. ठीक है, थोड़ा सा आप play around करें vectors के columns, you will find this. But isn't it saying R is the rank of A? Yeah, it's saying that A is basically a linear combination of R rank 1 matrices. Okay, that means I could drop some of the terms. Agar R is 1000, maybe I could take the if R is 1000 and I put them in descending order, then the ones that get very small, unko ho sakta I can ignore them, right? So maybe I can take the first 500 only. That will be a low rank approximation of the matrix A. And we do that. Can we do it? Yes, we do it often in image processing and in machine learning now also. This is the full matrix A. This is rank 1 approximation. That means I only took the first term, sigma 1. We normally write sigma 1, 2, 3 in descending order. Highest singular value को पहले लिखते हैं. That means that has the biggest contribution anyway. But alone it seems not enough. Yeah. Okay, I take two terms, sigma 1 A1, sigma 2 plus sigma 2 A2. That's a bit better, Already up to 5 approximation, rank 5 approximation, it's already beginning to look like the real thing. It has all the useful contours. It's just an idea. It's heavily used in reducing the amount of data to work with. Okay, so final thing, second last thing after that, just one formula. We have a new norm here. Norm याद है? Yes. कौन से देखे थे हमने? Manhattan, Euclidean, Minkowski, और Hamming, distance norm वगैरह. So related to matrices, we have a norm called the spectral norm, which is basically the largest singular value of a matrix. Okay, एक matrix की जो largest singular value है, we often use that in different results, and that's called the matrix norm. This is the last topic in matrix decomposition, which is can we kind of find the square root of a matrix? Yeah. Now this is very helpful in working with something that is going to show up a lot in machine learning. Yeah, that is the covariance matrix. Now the covariance matrix, when we come to it, I will talk about it in detail, but it by its design it is symmetric and positive definite. Okay, positive semi-definite. That means it has some special structure, and we often need to find its square root. Now we don't have a definition for the square root of a matrix, but there is something that can come close, is that firstly we require that this will only work if the matrix is symmetric and positive definite. If that happens, then we call it the Cholesky decomposition. A can be written as L, L, T, where L is a triangular. Yeah. So if L is lower, then LT has to be upper. Yeah. So we will see when we come to covariance matrices that splitting a covariance matrix into this helps us generate random variables that follow a particular distribution. Okay, it will be very useful later on, so it's good to have it in mind. This we will just say, okay, carry out a Cholesky decomposition to find L and use L to generate a random variate. आप लोग सिमुलेशन कर रहे हैं कोर्स, कुछ लोग तो कर रहे हैं, उसमें you generate random variates, right? So there it is. So that completes the topic of matrix decomposition.